last two at the bottom here.
Hold this.
The last two at the bottom here.
Last two at the bottom here,
Oh.
you notice, end up adding water to a double bond. Now, there's strange looking reactions, the reagents you've never seen before. So if you have this alkene and you want to add water to it, according to Markovnikov's rule, so the orientation of addition would be Mark orientation. So the hydrogen would go to the carbon that already has more hydrogens, and the OH goes to the other. I could do that with dilute sulfuric, but that's going to give me a mess. The reason it gives me a mess is that it's going to produce a carbocation, and carbocations are prone to producing all kinds of products. So, this, next to the last reaction right here, adds water according to Markovnikov's rule, but without producing a carbocation. That's the magic here. Now, it's a little bit expensive because it uses a mercury reagent. The mercury, you know that mercury can have a valence of +1 and +2. This is mercury 2, and it's the diacetate, mercuric or Hg2 acetate. Acetate is OC double bond OCH3. That's actually acetic acid without the hydrogen. So you've got two of those. And an abbreviation for acetate, because it's so common, is OAC. So if you look at it up here, it says HgOAC taken twice. So that's mercuric acetate. And then the second reagent here, NaBH4, is a boron reagent called sodium.
Hey, he said that. That's what it looks like from here. One row makes that much of a difference.
Borohydride. NaBH4 sodium borohydride. We'll see sodium borohydride several more times in different reactions. It's a very common reagent in organic chemistry. So the one means you add mercuric acetate and water. Now notice below the arrow there's a number 2. That style of writing reagents means don't add number 2 until number 1 is finished doing its thing. So this is not throwing everything in at once. And this is the style, so you have to learn to read it in reactions. Treat the alkene with mercuric acetate and water, and then when that step is over, add the sodium borohydride. If you throw everything in at once, it doesn't work. Now, what's going on here? Well, basically, the mercury, you know that the metals are Lewis acids. All of those transition metals like tin and mercury and lead, they're all Lewis acids. You learn that right at the beginning of the course because they have holes in the outer shell. So they're like a proton. And mercury will add to the pi bond, but not to form a carbocation. What mercury is able to do is sort of bridge over the pi bond and associate with it, and then water comes in, and there's an intermediate where the pi bond goes to this adduct. So a hydrogen adds to one of the carbons of the double bond, no, sorry, no H rather, from water. And then part of the mercury reagent ends up bonded to the other carbon. And what you do with the sodium borohydride is you replace this whole thing with a hydrogen. So the sodium borohydride can cleave the carbon-mercury bond and replace the whole thing with a hydrogen. So it's kind of a tricky reaction that gets around formation of the carbocation, but, and I'm not asking you to write a mechanism for this ever, but you should appreciate that the Lewis acid material agent is coordinating with the pi bond, and then water is adding what amounts to an OH, and then in the second step, the carbon-mercury bond is replaced by a hydrogen. So you end up with CHOH. The addition of water, yes.
The addition of the mercury acid.
It's like
is that
last
because of
semester in
stability reasons, so it stays
Chem lab,
stable
Gen
with
Chem 2
molecule?
lab.
Yes, it doesn't form a carbocation.
They said
It sort of
COOCH.
gets the pi bond ready for
That
the
was the
addition
actual
of
name.
water,
I was like
but
laughing
it
when I read
doesn't form a carbocation. So it's an end run around the carbocation.
That replaces the mercury with it's coming from the NADH3.
Yes,
So it
sort of.
becomes NADH3, or is it using it from the water?
Well, it's more complicated than that, but basically, yes. And you'll get a clearer picture of what sodium borohydride does in a later reaction. But it's really not important here. The point is that this is a way of skirting the formation of a carbocation, but it still adds water according to Markovnikov's rule. So rather than using dilute sulfuric, the chemist would use what's called oxymercuration demercuration. That's the name of the reaction process. Uric acid takes water in the first step, and then sodium borohydride in the second. But you still end up with the addition of HOH, where the H goes to the carbon that already has more hydrogens, and the OH to the other. Now, you would never do this industrially because you can't use that much mercury, and it's very expensive. So this is more of a reaction you'd see in the pharmaceutical research lab, for instance. Okay, so we have a way of adding water. It gives basically 100% yield. And just as an aside, by the way, this is actually a fun reaction to run, because what happens to the mercury at the end is that a bowl of elemental mercury falls out of the reaction on the bottom of the flask. So you know the reaction's over. It's like a red flag popping up, or the turkey's done, and the base, the little thing pops up, and you get this shiny ball of mercury in the bottom. Ends up as acetic acid. There's a lot to this reaction, but, and let me say, just a practical point, reactions that on paper can look very, very complicated and messy can be a real piece of cake in the lab. This reaction is no trouble at all. You just throw the reagents in, and within 10 minutes, this ball of mercury pops out, and you have 100% yield, basically, of the alcohol. This one, which is much simpler, dilute sulfuric, looks better on paper, but it gives you a god-awful mess that you have to clean up. Okay, now, we're still left with, synthetically, if you want to make alcohols a shortage, how do you make the other alcohol? where water would have been added in a sense opposite to Markovnikov's rule. Because if you think about it, the odds are 50-50 as you go along trying to make alcohol that you'd want one or the other. There's nothing special about the Markovnikov alcohol. It's just easy to make. What about the so-called anti-Markovnikov addition? And organic chemists, of course, are relentless in filling in those gaps. So it didn't take long for somebody to figure out how to do this. And that's the bottom reaction here. It adds water opposite or anti-mark
Can you see
to
that
the
that he
double
just drew?
bond. Now, it's a totally
Is that a
different
question mark?
set of reagents. What's going on?
Is that H, OH, and CH2?
Well, first the alkene is reacted with borane, BH3. You know, of course, that CH4 is methane. BH3, sensibly, is borane. It's a gas, but it's very easy to use. You can buy it dissolved in ether and just use it that way. Boron is a Lewis acid. Trivalent boron has a hole in the outer shell. So what it does is it reacts with the pi bond. Like any Lewis acid, the pi bond reaches out and forms a bond to the boron. And it actually does that to form the more stable carbocation. So in a sense, it's following Markovnikov's rule. The boron adds to the carbon that already has more hydrogens. But here's where I have to make a big admission. What's in the brackets there doesn't actually get a chance to live, because boron has a very unusual property, and the boron has a negative charge because it's picked up a pair of electrons from the pi bond. So the whole thing is neutral, but I'm showing charge separation here. Boron is able to slide over a hydride ion immediately. As the boron is forming a bond to the carbon, it's sliding an H minus over to squelch the carbocation that might have formed. So no carbocation ever gets a chance to form. The borane actually adds, in the end, BH2 to one carbon and H to the other. So there is an actual intermediate that you can isolate that has the borane added across the pi bond, BH2 to the carbon that already has more hydrogens, and H to what would have been the carbocation. This is called an alkyl borane. What you have is a cyclohexane ring with a CH2 attached to boron. Now, the magic of this is in the second step, which uses an oxidizing agent, hydrogen peroxide. Some of you should be familiar with that. It's a common biochemical reagent. Not water, but hydrogen peroxide. Hydrogen peroxide has the ability to oxidize a carbon-boron bond And we're not gonna replace it with a hydrogen,
Does
like
it
you
say
saw in the last
SYN?
reaction. But it replaces the boron with an OH. So by a tricky maneuver, it ends up adding water, and it looks like it violates all of the chemistry that you've seen so far. But when you drag through the mechanism, it's totally consistent with it. And the SYN part of it that's up there is because the boron and the hydrogen add from the same side of the pi bond. So when the boron becomes the OH, the water is added from the same side. Just a stereochemical feature. So it's called anti-mark with SYN addition. So I can add water with either the butyric acetate or the borane, either way, and get either of the two alcohols in basically 100% yield that correspond to the addition of water to an alkene. And adding water to an alkene is a very important reaction. Gets oxygen into a hydrocarbon. Okay, so you want to bundle these two reactions together. This one with dilute sulfuric is of lesser importance, but it's not hard to deal with anyway. Just think, I'm adding water through a carbocation and it follows Markovnikov's rule. But you're more likely to see this as a way of adding water according to Markovnikov's rule. This is called oxymercuration, demercuration. This one down here is called hydroboration oxidation. And it adds water, but opposite to Markovnikov's rule, with Markovnikov's rule in quotes, because poor Markovnikov never said anything about these reactions. We're just kind of stealing his rule, stretching it. All right, now there are two other reactions up here. One of them is very simple. This is the addition of H2 in carbon tetrachloride, and this is the addition of X2 chlorine or bromine in water. But they give different results. The carbon tetrachloride is the solvent. Now, we usually don't specify a solvent when we write a reaction, unless that's a clue to help you out. Because notice these two reactions look exactly the same, except for the solvent. One is CCl4, the other is water. And the products are different, so watch out. Carbon tet and chlorine is the simple case. This is the addition of chlorine to the carbon-carbon double bond. Now, Markovnikov's rule is totally unnecessary here because you're adding the same thing to both ends of the double bond. So it doesn't matter. However, there is a stereochemical feature to this reaction, and that is the chlorines or bromines, if you're adding bromine, end up on opposite sides of the double bond. It's an anti-addition. Now, in an open chain alkene, there's no cis or trans, so that doesn't matter. But in a cyclic alkene, it makes a difference whether the two halogens add from the same side or opposite sides. And the truth is they always add from opposite sides. Now, why is that? Well, the way this reaction works is the following. bond pair acts like a nucleophile, attacks the chlorine, and causes the chlorine-chlorine bond to break to produce Cl- as the leaving group, plus
And indicates that nucleophiles involved.
valence. Plus a new bond from carbon to chlorine, and I'll initially show it as a particular carbocation, but it never actually forms because chlorine is a very large electron cloud. And what chlorine and bromine uniquely are able to do is they smother the other carbon that would otherwise be a carbocation and protect it. So if there's a double bond here and the chlorine adds, the other carbon is supposed to be a carbocation, but the chlorine just reaches over and drops its electron cloud on top of that carbocation and smothers it. It's still there. It's still a plus charge, but it's kind of smothered by the electron cloud. It's what we call a bridge ion. So the chlorine is sort of straddling across the pi bond. Now the other chlorine then comes in, and it has to come in, that Cl- has to come in from the opposite side of that bridge. Once the chlorine bridges over and smothers the carbocation, that side of the ring is blocked. So the second chlorine always comes in from the opposite side of the first. And that's entirely due to this bridged chlorine ion or bromine ion. Both chlorine and bromine add anti. Just try to remember this bridging action, and it helps you to remember that it's an anti-addition. And that's all you have to remember for this reaction. If it's a cyclic alkene, the halogens add from opposite sides. You don't worry about Markovnikov's rule or anything like that because you're adding X and X. Now, what about this, the one reaction below it? Which adds, again, X2, let's use bromine in this case, but instead of carbon tetrachloride, which is a harmless, nonpolar organic solvent, we use water. Now this changes the course of the reaction in the middle. It starts out exactly the same way, where bromine adds to the pi bond, and you can just picture it like this. It's a bridged ion where the bromine is straddling the two carbons that used to be the double bond. But because of the water that's present,
What does that say? B1 half? Or BR2? Yeah. Thanks.
the water comes in from the opposite side of the bromine as the nucleophile. Not bromide ion, but water, because there's a tremendous amount of water present. Bromine is not very soluble in water, and neither is chlorine. So when you see bromine water or chlorine water, that's maybe only 1% of the chlorine or bromine in the water. It's all that's soluble. So it's mostly water. So the water takes over and becomes the finisher in the reaction, and the water always adds to the carbon that kind of follows Markovnikov's rule. Well, let me show you the product. Once the water adds, it then quickly loses a proton from the oxygen to give you an OH group there, an alcohol. So the bromine is added to one carbon, the OH has added to the other. They're on opposite sides because of the bridge ion. And because the bromine adds first, it adds to the carbon that already has more hydrogen. So even though there's a bridged ion, it prefers to initially bond, sort of like Markovnikov's rule, to the left-hand carbon, which is the one that has more hydrogens. Now this is the most complicated of all of these reactions because it has this anti-feature, which is a stereo specificity, three-dimensional specificity, and it has this orientation control where the bromine goes to a specific carbon and the OH to the other. A lot of students mess this one up. I admit it's a hard reaction.
Why doesn't C4 react and all the other reactions?
Because it's totally inert. There's nothing about it. That's a good question. The carbon tetrachloride on the left board is helpless. It can't do anything. It's just an inert solid, not a nucleophile. So the bromide ion, and there's a lot of bromide ion present because bromine is very soluble, or chlorine and carbon tetrachloride. Chlorine and bromine are non-polar because that's a perfect covalent bond. So they're easily dissolved in carbon tet, but not in water. So that's addition of X and OH. They add from opposite sides, and the X goes to the carbon that already has more hydrogens. Yes.
So when you have the bromine and the oxygen, the cycloalkane is going to be on opposite sides, but one is in the straight chain and the same side.
Well, in the straight chain stereochemistry, like anti or syn addition doesn't matter because it's free to rotate. But the orientation
Down
still
around
falls.
tag.
So the VR will go to the carbon that already has more hydrogen. Yeah, this is a cyclic alkene.
My concession stand.
Because the bond in between is freely rotating. Right. The anti-addition only gets baked in and frozen in the molecule when it's a cyclic compound. It can't rotate. If it's open chain, the VR and the OH just really rotating, so anti or syn is meaningless. The stereo specific feature would be expressed by saying that this is a stereo-specific reaction, meaning it produces a specific stereoisomer. In this case, whatever you get from anti-addition, and not the one that would be formed from syn addition. The syn addition product is the stereoisomer of the anti-addition product. This business of where the bromine and the OH go on the carbons